Hello, and welcome to another Binary Ninja live stream. Thank you for joining us this week. We've had a lot of back-to-back streams this week, recently, and I hope you all have been enjoying them. Last week we interviewed Marion. We talked a lot about malware, got some interesting takes from her, and then she showed off some cool visualizations for looking at programs by their call relationships. This week we have another interview for you. I'm very excited about it. He's got a lot of demos prepared for us as well. But before we get into that, I have a couple of announcements. This week we released 5.2. So go out and check that. You can download it from the client, just most recent stable or most recent dev if you'd like. And also go check out blog.binary.ninja to see what everything's about, what all the different features do, how they work, and a little bit about what's coming next too. I gave it a read just a bit earlier, and I think there's some interesting tidbits in there for everyone. And tonight's the last night to submit to Reverse. So if you've been thinking about giving a talk and you haven't been sure, just throw it in. We've got a bunch of submissions already, but by all means, anything that gets submitted tonight can still make it into the program. And we'd love to see all your submissions. So, without further ado, I'll be introducing our interviewee for this week. He teaches the Software Deobfuscation Techniques class at Reverse 2026. So if you've been curious about what that class is going to be like, or you just want to hear his thoughts, I hope that you'll stick around and join me with Tim Blazytko. Thank you for joining us today, Tim.
Hello, Kyle, and hello, everybody. Thanks for hosting me. Nice to be here.
Yeah, of course. It is an absolute pleasure. I know that it's a bit late for you, so I'm glad that you can join us from the other side of the world.
It's a perfect time zone for me, so.
Yeah, we all have our different work schedules. Um, all right, so shall we jump right into the questions then?
So,
All right. I should say, you are a trainer at Reverse, but you are much, much more than that. Is there anything else that you feel is relevant for people to know? Anything else that you're doing that you want people to know about? Anything like that before we get into
well,
the
I'm
questions?
doing a lot of reverse engineering for quite a lot of years. I did my PhD in formal program analysis. I'm working on code obfuscation, deobfuscation ever since that. We with a few other guys in Germany, we have a company Mproof where we build embedded obfuscation, like binary rewriting for embedded firmware. And besides, I also give trainings and do research and stuff like that.
All right, perfect. Thank you for that. So let's get into our first question then. What first interested you in deobfuscation and I suppose obfuscation?
Well, I actually started when I was around 12 or 13 and was playing games. I, at some point, started to notice that I have much more fun in actually cracking the games. Like in the early 2K, it was like no CD cracks and some bypassing license validations and stuff like that. That's actually how I started and got into that. And so I had so much fun doing that I continued doing that, started digging more into reverse engineering, did my bachelor's and master's on that kind of things, and also my PhD. So, like, obfuscation, deobfuscation always has been a topic for me since 20 years, more or less, right now.
Interesting. That brings me right to my next question. Then you must have seen some different trends over the years. I'm curious, what was your PhD in, and how have things sort of evolved from then? What led up to that research, and what have you seen that's been new since then?
Well, my research was not only about obfuscation and deobfuscation, it was more about different variations in program analysis and especially binary analysis. Like I did some research on fuzzing, I did some research on obfuscation, on deobfuscation, and also on bug triaging. But what all of these methods had in common was more or less that I was like working on simplified program representations that are kind of some semantic representations that then simplify analysis. You can think about it like abstract interpretation, which is basically a simplification of computations that allows you to reason more about specific program characteristics. And so I also did something else, like I was looking for more specific semantic representations of the actual program that is better to guide fuzzing, to better guide deobfuscation, and so on.
Okay, yeah, very, very interesting stuff. You said you focused your research on obfuscation, deobfuscation, fuzzing, and did you say backwards triage?
Bug triage,
Back
like root cause
triage.
analysis.
What was that?
Root cause analysis. Like if you have a
Oh, okay.
crash and you want to know what's the origin of the crash, like which source line you have to fix in the end, and is this and what kind of bug is that, and stuff like that.
Okay, very interesting. Um, I guess I can see, yeah, I see where those things are related. I was recently thinking about how you can represent a program as just every possible state it can be in, and what fuzzers are often doing is trying to find those invalid states, or I suppose transformations from valid states to invalid states.
Exactly.
Um,
So let me give you an example. Like if you know your domain quite well, you can always do like targeted analysis that allows you to extract specific program properties that allow
mhm,
you to reason about that. Like in the fuzzing example, we are looking at grammar-based fuzzers. The idea was to fuzz like script language interpreters and stuff like that, but without having a preceded grammar, like without knowing actually the grammar. So the idea was more that we use some string-specific combinations like concat, splicing, and stuff like that, and take the dictionary of like the strings command over the binary and stuff like that, and with that use coverage as a feedback to actually learn the grammar of the underlying programming language, such that we can automatically build like valid programs based on the interpreter, something like that.
that's crazy. That's really wild. What sorts of other semantics were you embedding into the fuzzer to help guide it beyond coverage?
Um, Coverage was the most important metric, but you have some quite interesting characteristic. Do you know a bit about fuzzers? So
A
with
little
the
bit,
bitmap,
but always
so
worth giving
basically
the audience a nice refresher.
yeah, true. So basically, in fuzzing, we have something a so-called bitmap, and this bitmap allows you to track which parts of the program, like which edges you already have seen and not seen. And the
Right.
idea is that we have some pruning characteristics on the input, like if the fuzzer found a new input, it triggers specific bits in the bitmap, which basically means it triggered some new basic blocks. And then the idea is how far can we delete some stuff from the input? Like, let's see, assume we have some random Python program, and which parts of the Python program we can delete such that the coverage remains the same. And that way, we basically can use coverage as a feedback to find like keyword properties of the underlying programming language.
Interesting. Were you then keyword coverage? So you were recovering like the high level semantics, the what type of control flow it was, or
It, yeah, it was more than you basically learn how the syntax of an ifs and else statement looks in
right.
Python, for instance,
Okay.
or stuff like that, or how a valid function call looks like, and so on.
Interesting. We have a question in chat here. How do you find input for your fuzzers in these cases?
That actually depends. In industry, you usually have some kind of large fuzzing corpus that you use as seed inputs and that you then randomly mutate. In our case, we started with an empty input and we're just generating random strings, and from that we basically build everything from scratch, or let the fuzzer build everything from scratch.
Right. To related to a bit of what you were talking about there, if you see like an input for a 64-bit number, you start with, okay, so it can be any of these 64 bits, which is an insane number of combinations to try on
Yeah.
something. But the hard work is trying to figure out how to narrow down what inputs to use to actually try. to see if they'll get you into valid states or invalid states or whatever it is, get you to crash.
Exactly.
So then finding those, yeah, those constraints to be able to eliminate like everything above OX7FFF, whatever, we don't need to
Mhm.
try. We know it's going to be below a certain value, for example.
Yes. However, in our case, it wasn't about like 64-bit inputs. It were
Hmm.
just entire text files as
Right.
input or something like that.
Which
Like,
is even worse.
yeah, until like a kilobyte of input or something like that or more.
Yeah, and I don't even want to do the math on the number of combinations you get out of that you could possibly put into a fuzzer as input. So you certainly need a lot of interesting things to be able to clamp down on those inputs. And trying to pull out hints from strings and such would be interesting. Did you ever work with like ML inputs for fuzzers? Were you able ever to get LLMs hooked into a fuzzer, or was that after you?
No, not really. That was LLMs weren't back then a thing there when I was working on fuzzing. It was in around 2018, 2019.
Right.
But basically, fuzzing itself is some kind of ML.
Oh,
It's basically some smart way of brute force. Like you use coverage as a learning feedback, and then you have this feedback learning loop where you just have like brute force, like raw execution time, where you have like thousands of inputs per second that you just randomly generate and put into the program, and then measure the coverage and see what's interesting, what not, and then you keep the interesting stuff and mutate that.
yeah, that's a good point. That fuzzing is ML. You are trying to, I guess, figure out the distribution of human inputs that
Mhm.
go into the or can go into the program. Hmm. I don't think I've ever really heard it described so succinctly, though. What got you out of fuzzing and more towards the obfuscation then? The game hacking?
No, not really. I was always interested. Like, I was mostly interested in obfuscation and deobfuscation.
Right.
But in academia, working on software protection, like obfuscation, deobfuscation, is quite a hard thing. So I managed to do two papers there, which most other researchers don't really are able to because you have to have really strong nerves because academia doesn't like obfuscation. Like the fuzzing papers, for instance, have been accepted the first time. The obfuscation papers needed like 5 or 6 iterations and stuff like that. So
Why doesn't academia like obfuscation and software protections?
obfuscation is security by obscurity. It basically makes just things harder to analyze. And it's hard to measure actually. And this is a property which is very, very uh, not liked in academia.
That is interesting. May stop me if I'm getting ahead of ourselves, but are there secure obfuscations?
No. There are good obfuscations, like in a practical manner, that allow experts to spend a lot of time and knowledge for several weeks or months to break something. So, but there is nothing like secure obfuscation, which is secure by design, which can be proven to be secure and stuff like that. This doesn't exist.
Very interesting. Why is that?
Um, I don't know. There is some research about theoretic obfuscation properties and stuff like that, but they all are very, very academic. So like it's and basically it's hard to see. But even if it would exist, it's like there's a large gap between theoretic stuff and practical stuff. Like even if there would exist something like as theoretically secure obfuscation, it doesn't mean it would be feasible in practice in any way.
Mm, yeah, it could reduce performance too much. It could
Yes.
increase compilation time too much. It could do any number of things to make it unfeasible, or it can just be too hard to implement.
Yeah.
When you're working with obfuscated code, how often are they like these robust projects that have been robustly obfuscated versus just some simple instruction substitution or whatever it is?
That mainly depends what and where you're looking at. So let's say we are working on some hobby projects, some hobby obfuscators. These are more just toy examples and might work on specific examples and don't work on others. Then we have the category of malware, like malicious code. There you find a lot of obfuscation, but they are mostly like quite common obfuscation or custom, but they are like low-key or middle-class obfuscation. You have some basic control flow flattening, some control flow obfuscation, some simple stuff. And this might work most of the time. High-end obfuscation, like the good stuff, the hard-to-break stuff you also have in the commercial areas, like in multimedia, in DRM systems, in gamings, in anti-cheat engines, and stuff like that. So basically everywhere where there's money inside the market.
Mm.
There you have very hard stuff.
Mm-hmm.
And at the same time, if let's take for instance gaming as an example, where a game or a protection must run on millions or 100 millions of machines, there it must be pretty stable and shouldn't trigger side effects like strange environments, crashing, increasing overhead, and stuff like that. This shouldn't happen there too much in that area.
Right. Someone is asking in chat if we're going to show a deobfuscation example. We will at the end. Stick around.
Yes.
We've got some cool demos coming up. Um, but you talked about a lot there. You talked about a handful of different types of obfuscations, where those obfuscations might be used. Do you mind elaborating more on the role of obfuscation in security?
Sure. So obfuscation, the idea of obfuscation is to impede reverse engineering. Like the idea is obfuscation basically transforms or rewrites the code in a way that it looks very complicated, very unintuitive, but computes the same. Let's say you have a Fibonacci implementation, which is just 20 lines of code. And if you look at that, you know, oh, it looks like Fibonacci. But if you obfuscate that, it might look like really crazy stuff, like
Right.
hundreds or thousands of basic blocks or across different functions, lot of strange encodings and stuff like that.
Pretty sure
If
I've
you look
seen
at
this
that,
in
you
a
see,
CTF challenge before, for sure.
yeah, and then you take a look at that and see what the fuck is actually going on there. So you look at the code and don't have any clue what's going on. But if you execute it, it still behaves like a Fibonacci.
Right.
So it computes the same, but it looks just crazy. That's obfuscation. And so the question is, where is it actually used? I also mentioned some examples. So basically, malware, commercial stuff, but you can in general say obfuscation is used everywhere where some form of anti-reverse engineering is intended, or where you want to protect some intellectual property, like to make hard malware analysis harder, to win some time,
Mm.
to make your sales window larger. Like if you in the gaming, you don't want to your piracy your software to be cracked in the first days because this is your largest sales window. So you want to obfuscate the license validation and stuff like that. If you are in mobile and you look at banking apps, you have a lot of obfuscation in there to hide the computations in the background. If you look at like mobile apps from the big companies, like the social networks and stuff like that, they have a lot of obfuscation in there to obfuscate how they use their internal APIs because they don't want that others use their internal APIs, but they're public APIs instead. You
Oh,
have
interesting. Okay.
digital rights management, like watching Netflix, watching movies, watching Blu-rays, where you have a lot of encryption and decryption that is heavily obfuscated, and so on. So basically, you have a lot of different areas where obfuscation is used. And another area where it is used, which is quite exotic, but happens from time to time, is to make bug finding harder. Like if you know that a specific code is full of bugs, you could, or some people then use obfuscation as an additional layer to make bug finding harder.
Very interesting. The one that you mentioned in there that I think is most surprising to me is gonna be decryption and encryption. I know that there's some obfuscation around encoding and decoding because there's like proprietary
Mhm.
encoding and compression algorithms. But why would, if a encryption algorithm is secure, why would that need to be obfuscated as well?
You might want to hide which kind of algorithm you use. You
Mm.
might want to hide your initial seed that you use. And sometimes, in some cases, you also have to hard code like a private key, like a private RSA key, or semantic key and stuff like that.
Or other
And
constants, yeah.
constants and stuff like that in these cases, but also to make, like, if you know as an attacker where to intercept. Let's say you want to you want to dump your Netflix key and decrypt on your own, and you know where you can set the breakpoint, where you can dump stuff and decrypt it on your own and stuff like that. So also this shouldn't be possible.
Yeah, no, that makes a lot of sense. That's very interesting.
Yeah.
I guess the in the middle part would it makes a lot of sense. Yeah, someone's saying
Yeah.
here to prevent
And
your hooking into encryption as well. Yeah.
yeah. And it's not always obfuscation, it's always a mix of passive and active protections. Like passive protection is obfuscation, but then you have also anti-emulation, anti-debug, anti-tamper, code checksumming, and stuff like that. And these go hand in hand.
Yeah, yeah, as anti-reversing techniques in general, you mean?
Exactly.
Yeah. Yeah, it's interesting to think about obfuscation as specifically an anti-RE feature because there's a lot of ways to prevent people from reversing code, one of which being obfuscations. But you also mentioned protecting IP, protecting like private APIs and all sorts of just whatever people want to hide in their code would be the purpose of obfuscations. Um,
Uh,
But then, what is the purpose of deobfuscation? If we're trying to make software more secure by preventing people from being able to hook into it and change it and steal these things, re-implement things, then why do we need deobfuscation as well?
so it always depends who is doing deobfuscation. So there are many ways to do deobfuscation, or many motivations. One of them is of course cracking or piracy. So people protected their stuff such that piracy is harder, but you have then the goal to still crack it. So you want to analyze it and bypass it. Or you want to still steal the IP because it's your competitor that has great know-how that you want to steal and copy. So your life is harder now, but you can still do it. So this is one thing. Then the other thing is like malware analysis, like where you have like legal reasons to analyze code and to understand it, because it might be malicious.
Mm,
Then you have something like a lot of cheats themselves are obfuscated. And so in the gaming industry, it's quite common to deobfuscate cheats such that people understand how to detect them.
I see. Okay. So it's
And
vital to do a bit of analysis or deobfuscation on obfuscated code just to make
yes,
sure that it's safe, just to make sure it's not malware.
exactly, for instance. Or how the malware works. Like the malware, let's assume you piece of malware, it contacts CMC server.
Right.
So, but this URL is computed at runtime,
Mm.
and it depends, like the domain generation algorithm, like it uses specific inputs and computes the domain based on that. And this part is obfuscated. You want to know how the fuck does the domain generation works. So you have to dig into that.
No, that makes a lot of sense. Thank you. Yeah.
And one reason, of course, is also like cat and mouse, offensive, defensive. To build good obfuscation, you have to know the state of the art, how to break stuff. Like, no good obfuscation without knowing how to break it.
That leads us into one of the user questions here, or I guess viewer questions here. What do you consider the current state of the art for obfuscators, for the sectors you mentioned, like DRM and gaming?
Um, this is a good thing. Like it was 2022, I think, where we did some research and also gave a recon talk about the current state of the art in obfuscation and deobfuscation. Basically, the talk was called like next gen virtual machine based obfuscation. It's also linked on my website.
I'm just trying to find it for people so I can throw it in chat.
Yeah.
Recon 22, next generation of um, virtualization.
Yeah, maybe we can show it live in the live stream for a minute, such that people who watch the stream also see that.
Here, I just put it in chat for everyone to go check out if they want to, as a more comprehensive answer. But I can bring it up. If do you have it up on your screen?
Not right now.
If there's anything in particular you want to show off.
No, I have.
All right, there we go. We can see your
So
screen.
basically, this is my website, synthesis.to, and there you find all of my talks and stuff like that. And here in 2022, there's this talk, the next generation of virtual machine-based obfuscators, where you find the slides and the recording. This is it basically. So in a nutshell, it uses a lot of global obfuscation and use thousands of instructions where that have to be eliminated in a row and stuff like that. So a lot of stuff which enforces a global analysis instead of a local analysis. This is more or less a quintessence there.
While I switch back to our cameras,
Yeah.
I encourage everyone to go watch Tim's old talks. He's given a lot of very interesting talks that every single year at Recon gives me another plugin idea or several to write for Binary Ninja. So definitely go check that out. I have another question here. We've been talking about the obfuscations you can make, and then of course, if you can identify that obfuscation, you can make some state-of-the-art deobfuscators. But if you can detect those obfuscations, then endpoint management systems can also detect obfuscated code. So the question here is, isn't obfuscation flagged by endpoint detection systems, and how do you avoid that?
It hardly depends what is obfuscation and how do you want to detect obfuscation. Like there are some characteristics that are easy to detect. Let's think about self-modifying code, where code rewrites it at runtime or unpacks it at runtime. Like you have a dedicated section that is maybe mapped writable and executable, and then you modify it at runtime. Something like that is easy to detect, of course. But what about code that just looks complex, like a complex state machine, data processing logic, and stuff like that? How do you want to distinguish that one from normal network protocol logic or
Hmm.
something like that? So, as a reverse engineer with some experience, you can easily do that, but in a automated way, there's just no way to do that. Otherwise, you would have like thousands of false positives.
Yeah, no, that makes sense. It boils down to the heuristics you can make about it, and you can always hide obfuscate. You can always make obfuscated code sort of look like legitimate code, right?
Yes,
Make it
exactly.
look like something else. That's honestly the point of a lot of obfuscations, to make it look like something else.
Yeah, it's not hard. In most of the cases, like in 90% of the time, it's easy as an with a trained eye to detect obfuscated code.
Hmm.
But but generalizing it in a way that it doesn't have false positives in a fully automated way, this is a very hard thing.
Elaborate on that. What feeds into your intuition when you're looking at something and you think it's obfuscated? What usually hints you towards that?
Well, obfuscation always follows some patterns obfuscation is automatically generated code that uses a rule system that is somewhat static to some extent at least. And so it's like you can recognize compilers because they have specific characteristics and optimizations. You can pinpoint obfuscators. So if you take a look, and you can easily identify binaries of the same obfuscator. And if you have multiple obfuscators, you can still see that it's obfuscated because it doesn't look like normally compiler-generated code, or it uses some weird stuff, like it uses custom calling conventions, it has complex graphs which follow a pattern that's not common in typical network protocols or stuff like that. So if you reversed the one or other program, it's easy to notice. But if you didn't reverse a lot, of course, that it's harder to distinguish.
Interesting. So if you have a new obfuscation and you have a binary with that obfuscation applied to it, but you have no other samples, is it hard to figure out that it's been obfuscated and what it's doing without having those other samples to compare to?
That indeed highly depends on the kind of obfuscation. If it's more low key, if it's high key. If it's high key, it's very, very hard to do. If it's low key, or like if you see it's just some basic control flow obfuscation, where that it's easily removable, then it doesn't make much of a difference. But
Have we walked through the different types of obfuscations for people yet? You've mentioned a
no, not yet.
handful. Do you mind walking through some of them for people?
Sure. So basically, we have something which is data obfuscation and code obfuscation. So with data obfuscation, I not necessarily mean just encoding data, but also encoding basic obfuscations like encoding stuff like in an arithmetic complex way, like arithmetic obfuscation, or the other thing is control flow obfuscation. In control flow obfuscation, you basically make the control flow graph significantly more complex, or
Hmm.
you make it weird in a specific way that you cannot easily see the structure and what's going on and stuff like that. We will have some examples of that later today in the demos. So we have like control flow obfuscation, we have arithmetic obfuscation, and we have virtual machine based obfuscation, or VMs. So, and these are especially VMs are the more powerful obfuscations in terms of there you similar to Java or something like that. You have entire software interpreter with a custom CPU instruction set that you don't really know, and then you have a piece of machine code written for that virtual obfuscate for this virtual interpreter, and to identify or to basically be able to analyze the obfuscated bytecode, you first have to analyze, reverse engineer this entire interpreter, write your own disassembler, and then put the bytecode inside that, and then start restructuring the control flow, and so on and so on.
Right,
So these are the most common obfuscation schemes. And of course, you can mix all of them in weird ways.
right. Yeah. I've certainly looked at VM obfuscated code before, and it is very obnoxious because you're not only reversing the code, but then you're reversing the code executes, or the code that executes the code you care about, depending on which way you're viewing it. All right. So we've talked a lot about deobfuscation. A lot of this is based on top of being able to pop open a binary, look at the instructions, see what they're doing, maybe be able to rewrite them even. So a lot of this is built on top of reverse engineering. I'm curious, how would you define reverse engineering? How does it serve what you do? And what does a good reverse engineer need to know to get into deobfuscation?
Well, first, what is reverse engineering highly depends on the goal and the setting.
Yes.
Like, we have file format reverse engineering, we have binary reverse engineering, we have that, we have that. So, and your goal is also very different. Sometimes you want to know just only what the code might do. Sometimes you want to look for specific functionality, like where's the license validation and how does it work.
Hmm.
Sometimes you want to know just what functionality would this code have, like you have a piece of malware, and maybe what API function does it import to learn about its functionality. Sometimes you just want to take a look at the strings. So it always depends on the use case. Sometimes you want to find bugs and do VR or vulnerability research. And with that, you have different ways and strategies what you're looking at. So typically, what you are looking at is some specific characteristic you are interested in, and you want to extract that from an unknown file. Like you have an unknown binary, you have a goal, and you want to extract these information from that.
And your
And
goal
that
is
is,
going to be, is this malware? Or how does this work?
yes,
What APIs are they calling? What URLs are they accessing? Stuff like that.
exactly.
Any
And so
semantic property, as we like to say.
yes, and so in a very generic way, you can define reverse engineering as extracting valuable information from an unknown binary. And whatever valuable is depends highly on the context.
Interesting,
And
yeah.
that also then depends on your strategy. Like most of the time, you fire up Binja, IDA, Ghidra and load the binary in. So then you might take a look at the strings and at the API imports to find interesting data that give you a good clue what is going on. You follow cross-references, analyze the data flow, dig into that, and then sometimes you want to understand it in detail. Then you have to dive very deep into that. You have to recover types and data structures and stuff like that. You have annotate variables. Sometimes you want to just get a high level feeling what's going on and then okay that okay then you're done and stuff like that. So it always depends.
So I'm sort of feeling that the answer is if you want to get into deobfuscation, you have to be a really good reverse engineer first to be able to do the type deduction, track data flow, all those sorts of things.
In fact, I wouldn't say it like that, but at the same time it's kind of true. Like there are a lot of good reverse engineers which never worked with obfuscated code.
Sure.
And if they fire up a binary in their tool of choice and they see it's obfuscated, sometimes their first reaction is, oh shit, and just close it and
Mm,
go to another binary. So there are a lot of skilled reverse engineers who never dealt with obfuscated code and think in the end it isn't really too hard. As a reverse engineer, you are used to recognize patterns, to work with your tools and stuff like that.
right.
And the thing which obfuscation introduces is mostly unknown patterns. You look like you know your function prologue, you know a function epilogue, you know how a stack canary looks like and stuff like that. But you might not know this weird construct that you see all over the place. But you see it a lot of times. So you start figuring out what's going on. Where is it used? How it is used? How often does it occur? And stuff like that. And then you might be able to, oh, okay, this is all over the place. This is used in this context. And then you learned an important pattern. And once you learned one pattern, you start looking for other patterns. And then you try to understand them. So it's more like pattern recognition, pattern matching, and then making some sense and connecting the dots. And
Okay. Yeah. Don't mean to interrupt you there.
yeah, and this is where it gets hard is or significantly harder is if there are use different patterns or if there are so many things that you're enforced to script stuff and stuff like that, like large scale. So this is where it becomes very time consuming, but
Yeah, no, that makes sense.
yeah.
It sounds like then even you don't even necessarily need to be a good reverse engineer to get into the obfuscation because you just need to be able to start recognizing those patterns. And as
Yeah,
you're getting
it's
into
more
reverse
like
engineering,
you
yeah.
have to be open-minded
Mm-hmm.
about finding new patterns,
Yeah.
and this is basically the main challenge that you need to do.
I think learning reversing in general is a lot about just learning why things are the way they are. And the answer
Yes,
for that is usually open the Intel handbook and find the thing somebody wrote in the 80s about why that is the way it is.
absolutely, yeah.
But a little bit less so in obfuscation. Um, some of the patterns I've seen, one of the patterns I have sort of learned to recognize in obfuscation are going to be sort of like repeating recursively applied substitutions
Hmm.
as a instruction level obfuscation. Instead of an add, make it an add and a subtraction. Just replace it with
Hmm.
an identity. Um, but what other sorts of patterns are you finding? Have you learned to identify over time? Um, I
Well,
guess
it's
is yeah.
often, you can think about it, what makes analysis hard, it's often complexity.
Mm-hmm.
So complex control flow graphs,
I see.
with repeated computations, some very weird instruction sequences or weird computations, or very long basic blocks, or additional layers, like in the case of virtual machines, where you have like a CPU in a CPU, kind of that, with some dedicated data structures, and you have to
I
figure
see.
out the connections.
Okay, so it's a variety of things, but some
Yes,
level of indirection or just knocking up the complexity for seemingly no other reason is often what you look
exactly.
out for. Interesting.
Yeah. Then you can also, like, you can, on x86, you can create like broken disassembly by jumping into the middle of other instructions. You can work a lot with indirect calls and basically hide jumps from A to B and stuff like that.
There's a lot of chat history here. Sorry, don't want to get too many things lost. As we're talking about what it takes to get into deobfuscation and obfuscation, somebody is asking, do you have any recommended reading lists or watch lists? I know we've already brought up your website and your history of talks before, but anything else beyond that?
Well, on my website, I also have some the talks and some blog posts that are quite interesting. And otherwise, Rolf Rolls, who's also a very famous reverse engineering legend, he did a lot of great stuff on reverse engineering and obfuscation and deobfuscation in the last 20 years. So I would also check out his work. And also, there's a French company, Quarks Lab, which did a lot of stuff on arithmetic obfuscation. They also have some good resources in their blog posts. And then there is Secret Club, which is a collection, which also has a good collection of blog posts related to anti-cheat engine analysis and stuff like that. So these are some pretty interesting reads.
Amazing. I'll have to check some of those out. Thank you very much. Um, I think I have one last question in chat here. So if anybody else has any other questions for Tim, make sure to get them out now. Otherwise, we just have a couple left and then we'll switch over to the demos. But this question from chat I want to highlight here is, would you say that defenders have the advantage um, or the upper hand over people attacking the obfuscation? So is it easier to deobfuscate than it is to obfuscate?
Mm, that's a good question. And in the end, it depends on the obfuscation, how good it is. Um, let's say if you write a good obfuscator, you add a lot of randomness and hard constructs and a lot of diversity, such that repeated obfuscation runs of the same input binary result in entirely different representations. So if you then, as a deobfuscator, broke one binary, it doesn't mean you can transfer your knowledge and tooling that you just built one to the another sample. So if done right, I wouldn't say so. If you use always like a deterministic obfuscation with the same kind of properties, less randomization, and also very simple techniques, then the obfuscation is significantly easier. Um, as an obfuscator, or you have a great advantage compared to the deobfuscator that you know the input. You basically know the plain text, and based on the plain text, you can build a lot of cool stuff that use properties of the original code, which is obvious for the obfuscator and unknown for the deobfuscator. So if done right, obfuscation can impede or can make the life for the deobfuscator very challenging if you use the right properties and characteristics.
Very interesting. Yeah. One of the things you mentioned earlier was that obfuscation serves the role at times just to protect the sales window. So
Hmm.
the defenders, in a way, do get a advantage in that they have all the time in the world that they need to deobfuscate the code.
Yes.
But the attacker, the people who release the game, whatever it is, still get that time that they were trying to get out of it. And you can always change obfuscation techniques. You can always rotate between a few if you really need to, right?
Exactly, especially most people who do obfuscation as a business, or you have an in-house team for that, have something like rolling releases, rolling obfuscation schemes. Like for a specific time window, it's the specific obfuscation, and then it changes, it evolves over time and stuff like that. So like, if you take a look at the game last year and the game this year, you probably find a different kind of obfuscation.
That's very interesting. How quickly does the landscape move then?
It depends always on the context and stuff like that. So let's take, for example, De Novo. There was a time, De Novo, one of the large game protection companies, there was a time where a lot of games have been released for them or have been cracked just nearly after game start or game publishing time.
Mm-hmm.
And like nowadays, I think I looked it up like 2 or 3 weeks ago. I think none of the games of the last year of the last 18 months or something like that has been cracked. So
Hmm.
they so and it's also a bit about strategy.
Yeah.
Like you have to only ship what you know is hard enough. You don't always have to take out the big guns,
Right.
because then you basically would showcase everything that you have. You can only bring out stuff where you know people will struggle. And in case you have the feedback loop, in game cracking, you have a feedback loop. In other areas, not necessarily. But if you have the feedback loop and you see, oh, people are catching up, then you just put out the next best thing, and so on and so on.
That's funny to think that some of these obfuscators don't really get the feedback of what they're defending against, but with video games, you can clearly see if there are more people
Yes,
playing than there should be.
yeah, there are many scenarios where you don't get feedback. Like
Mm.
if you look at embedded security, for instance. So, if you have like one competitor who builds a very good thing and sells it somewhere to the world, and some country looks it up, opens it, rebuilds it, and sells it on another store, stuff like that, you don't necessarily see that. And even if you see that as the company who builds the original product, you might not have an interest to make it public.
Right, yeah. You mentioned that you work on or have worked on embedded devices a fair bit in the past, right?
Yeah, still. So we at Improve, we work on embedded security, and we basically build binary reverse engineering, no, binary transformation tooling to add or to harden basically embedded firmware and add obfuscation, containment, isolation, and stuff like that.
That's pretty cool. I'll be honest, that sounds awesome. Somebody in chat was asking about like hardware reverse engineering works. We're talking mostly about software reverse engineering and obfuscation, deobfuscation. Have you ever run into hardware level obfuscations you've had to work around, and how do these two different things interface?
Well, at Improve, we do and have a lot of knowledge about hardware reverse engineering. Some of the other guys have did a PhD in there, for instance, and we have a lot of knowledge in there. And we sometimes work on the hardware and the software level. But personally, I'm personally a purely software guy, so I don't feel comfortable talking about hardware reverse engineering. It would immediately be wrong.
Fair enough. It's one of those things I've found interesting myself for a very long time. But it's expensive to get into and very difficult. I've
Exactly.
always been jealous of those people who have the devices where they can break down every layer of a PCB, take the images, and then follow some time. But it's hard. It really is hard. Let's see. I also want to ask where to start for all this, like obfuscation, deobfuscation, firmware, reverse engineering. I think this kind of relates a little bit to there are commercial obfuscators out there. What
Yes.
are the main ones? How do they work? Who's allowed to use them? Can you just go out and buy these things? Like, what's going on with that? And then, like,
Also, the answer is not that straightforward.
oh yeah,
So,
yeah, go on.
yeah. So there are the most well-known obfuscators out there are virtual machine-based obfuscators like Timida and VM Protect. These you can just Google and you will find them, and these are commercial products you can buy. Um, and then you have like platform specific or target specific obfuscations that basically companies that build obfuscation as a service that you don't really have access to other if you're not paying a lot of money, and then you still don't get access to the obfuscators, you just use it as a service. But if you want to get started, there are a lot of basic obfuscator. Like if you Google like LLVM obfuscator GitHub, you will find like 10 to 50 different projects which use compiler-based compiler plugin for LLVM, where you can just enable stuff, compile your own code, and obfuscate it with that, and play around and dig into that. So doing something like that is a really good starting point to play around with obfuscation.
Would you recommend LLVM passes in general as a way to experiment with obfuscation and deobfuscation, or
Not in writing. If you
okay,
start writing LLVM passes on your own, you will change your subject pretty soon.
fair enough.
Um, so playing around with LLVM-based obfuscators is quite common. So this is a good thing. That basically just requires you to build LLVM in a specific way, which is then described in the plugin repo. So something like that, and this is a good start. But if you start with writing compiler passes in LLVM, you probably will hate your life pretty
Yeah,
soon.
yeah, not the easiest API to work with. Unlike binary ninjas, of course, where it's easy to rewrite RILs, I would hope. Um, all right, so there is somebody talking a bit about FPGAs in chat. And have you ever worked with a device that's like changing its architecture on the fly? Anything crazy like that? Or
I've thought about that, but I never worked with that directly. But as said, I'm not a hardware guy.
yeah, I think once you get to FPGAs, you basically gotta treat everything as its own
Hmm.
device and platform and build your decompilers, disassembler pipelines for them. Built a plugin for Binja to lift things. I have heard once of somebody who, like every 2 weeks, they get a new target and it's a new FPGA with a new architecture on it, and they need to build a new architecture module and then start reversing. So yeah, when you get into some of this high level crazy stuff, you need to do some high level crazy stuff yourself to combat it. Which I think actually serves well to start to segue towards your demos. Because you've been working with obfuscations for a long time. You've been working with decompilers for a while as well. I suspect that there are some obfuscations you wish the main tools automatically handled for us. And I also know that there's some extensions you've written to let those tools handle those obfuscations. So I'll just let you take it away from that. If anyone else has any other questions in chat, feel free to keep them coming. I'll
In
interrupt
between,
Tim
just
as
let
I
me
see him.
say, I
But yeah,
don't
go for
think
it.
there will ever be something like a generic deobfuscator or
Hmm.
something like that. Obfuscation, as said, is by introducing new patterns, and deobfuscation is by writing custom tooling for those patterns and undoing it. And if you write them generic enough, you can tackle a lot of stuff, of course. But obfuscation by design is built in a way that it breaks existing tools and techniques.
Right.
And if you build a deobfuscator for that, somebody else will analyze the weaknesses there and build better tooling. So generic deobfuscation is nothing such a thing.
Sure. It's always arms race, always trying to chase the other side of it.
Yeah.
Yeah. All right. Well, let's check out what you've been working on then, if you're ready.
Sure, ready to go.
All right. I'm gonna switch to your screen then. There
Okay,
we go.
thank you. So I would basically like to discuss two different kind of topics. The first thing is basically how to detect obfuscation, and the second thing is basically how to analyze obfuscation. This is a small example. Will be a small example there. So to detect obfuscation, let me give you a scenario. So the scenario is not, it's not malware, it's like a commercial application. A commercial application where you don't obfuscate everything because obfuscation introduces overhead, it makes the code bigger, it makes the code significantly slower. So the idea is that you only protect important parts. So, and what is important depends on the goal. Like maybe it's your license validation scheme, maybe it's your high quality research algorithm, maybe it's just some cryptographic data, whatsoever. So, but overall, you only let's assume you only have something like only like 5 to 10% of the code base is actually obfuscated.
Okay.
So
So it's not that common you're seeing entire code bases obfuscated.
no, absolutely not. In malware, it is quite often the case, but in commercial applications, it nearly never is the case.
Oh, interesting. That feels a little bit silly to me almost. Why don't they obfuscate everything? Why do they only, make the things obvious that they're trying to hide?
Well, sometimes, or in most cases, obfuscation has like overhead factor of a few hundred
Yeah, okay.
times.
Right.
So if you are doing your real-time application or you're gaming, you don't want it to be 500 times slower.
All right, fair enough.
But if your game takes up 100 times longer to boot because it's just a few milliseconds more, nobody really cares that much. Just to compare.
All right, interesting.
So you only have a small portion of the code which is actually obfuscated, and you have basically the idea. The idea obfuscated basically implies interesting. So
Mhm.
there has somebody to hide, so you want to take a look at that. So there are many ways for that. Maybe you want to find bugs in there, maybe you want to crack something whatsoever, maybe you're just curious what's going on there. So the question I had some years ago was basically how to actually can I find obfuscated code in a large code base. Like I have a 50 MB binary, I have a 5 MB binary, I have a 200 MB binary. 5 till 10% can be thousands or 100,000 of functions that I don't want to pick one by one and take a look at
Mm,
that.
right.
Also, looking at strings or API functions, it doesn't tell me like obfuscated code print here, something like that. So doesn't work. So the idea is that we need to come up with some ideas how actually obfuscated code might look like. And there, something comes into the game that I was just saying today in the beginning. Obfuscation is often complex, like complexity, or it's weird, like uncommon code or stuff like that.
Okay.
So, and then the idea is that we are basically need to pinpoint or specific graph patterns or whatsoever. And then the idea is that we want to develop something pretty cheap that allows us in no time to classify all the functions in a large binary that have characteristics like that.
Okay, so
So
complex by some metric, weird by some metric, or
exactly,
one of some number of graph patterns we've seen before.
exactly.
Okay.
So what can be complex? The control flow graph. So what can also be a complex? Large basic blocks. So let's assume, just for example, let's fire up an unobfuscated program ls from core utils. So let's take a look at the assembly code. So we see a common basic block is pretty short, like between 2 and 10 instructions,
Right.
depending on the
Okay.
binary. If you now have basic blocks which have like hundreds of instructions or stuff like that, you have a pretty good indicator that this, for example, might be obfuscated. And if it's not obfuscated, it usually implements something else which is interesting. So maybe your large basic block with thousands of instructions is unrolled crypto instead of obfuscation. But still, finding unrolled crypto is also pretty interesting to look at.
Oh, we are getting
Then,
a request to share the samples. This is just, yeah, thank you, /bid/ls. We're just pulling up a random non-obfuscated binary.
yeah, but all of the samples I will showcase, they are also public in 2 repos I will just showcase in some minutes.
Perfect. Okay, cool.
Yeah. So, yeah. So basically a common function is quite small, doesn't have too complex code and stuff like that. So, and we might then have like, let's take a look. This doesn't, of course, hold for every function. Let's take a look at the main function. Well, this is a bit more complicated.
Yeah. And some
And
longer
this,
basic blocks
yeah,
in there.
but this is actually interesting logic. Well, this here, this is a state machine.
Yeah.
This is like a while true loop with a switch nace dispatching in between, where we have like a lot of different states, which then jump back to the dispatcher here. And based on some characteristic, we perform an indirect jump and jump to one of n different states. Like a graph like that can be like network protocol logic, file parsing, whatsoever.
Yeah, we
But
like these dispatches because they indicate to us it could be a statement, it could be one function calling a bunch of other functions. But
yes,
they indicate some significant amount of logic being or going on
yes.
in the program.
But there's also one obfuscation technique which always looks like that.
Oh, interesting.
And this is called control flow flattening. I'm opening an emoted sample like the malware sample.
All right.
And I just take a look at some nearly random function and take a look at the control flow graph. And you see quite a similar pattern. Like here, you don't have you have nested based, tree based dispatching, but still you have like this large while true loop with different states which are getting dispatched.
Interesting. So that is obfuscated, what you were just showing
This
me.
is obfuscated code, yeah.
Okay, I never would have guessed just by looking at it from here. It looks pretty normal.
So yeah, so the question is, this is control flow flattening. So the idea here is that we basically hide the control flow. Normally, if we have a normal if then else, like here, like for instance, let's take this code here, for instance, something like that. Here, we know this is code. We have an if then else. So this code goes, this basic block is executed first, and then that one or the other one. So we can, by looking at the graph, we see what's going on. And the idea of control flattening is to hide the actual control flow, the connection between the blocks. So normally this would be one block, this would be one state, and that would be one state. But is that state, this one, or this one executed first? You don't really know by looking at the graph. So question here would be, how do you distinguish a normal while true logic loop like this one in LS from control flow flattening like that? So the answer is, if you look in the decompiler output, you will see what's going on. So what you see here is that we basically, in this while true loop, dispatch control flow. We have initially here a variable EAX, which is set to some random value. And this is basically the control flow state. And then you see that we start dispatching that state and compare it against all kinds of variables. And then we are looking for that variable with this, let's just highlight it. We're looking for that variable, find it down here, and then we know, okay, this state here is the state which is executed first. And then we see it sets the control flow state to that value. And so by looking for that value, we would then find the second state which is executed, and so on. So control flow flattening basically encodes control flow in a state machine in a while true loop by setting the control flow, hiding the control flow in a dispatching based variable. And coming back to my plugin, this is a very specific graph pattern, like pinpointing graph structures. So one of my ideas was, by pinpointing obfuscated code, is to pinpoint state machines, like graph-based state machines, that allow that because they might either implement control flow flattening or they implement some dispatching logic, which, depending on the reverse engineering scenario, might be still interesting to look at. Because this might be a complex network protocol, this might be interesting for vulnerability research. Or this might be a CNC server communication in malware and stuff like that. So by pinpointing state machines, we have a good characteristic to pinpoint interesting code. So I think I started with that in 2020. There is this Binger plugin called obfuscation detection, which, as said, has been built with the goal to detect obfuscated code. But given the one example, it can pinpoint all kind of stuff, like string decryption routines, cryptographic algorithms, protocols, obfuscated code, and stuff like that. And one idea here is that it also can pinpoint like flattened functions or state machines. The idea for that is that it basically checks that it basically compares each function or walks over all functions in the binary and checks if there's any loop which has that kind of structure. And if so, we get a result. Let me showcase that on LS.
So sorry,
So here,
when you say that structure, you mean a loop with a variable defined at the top with the special constants you were showing us,
no,
or
no, I was more like a while true loop with a lot of different states.
okay, okay,
So for the people who do a bit of graph theory, we are basically looking for functions that have a loop where the loop dominates a lot of different children in the dominator tree.
interesting, okay.
So, and with that, we can, for instance, then, like we have, how many functions do we have? Let's check.
Functions plural.
Yeah, so we have 200 functions, not too much, but still. So what we can do is here, this window will be important. I go to plugins, obfuscation detection, and then do flattened functions. And then I get a list of functions sorted after this criteria. And if I pinpoint the first ones, like this one, I find a function which has exactly that form. If I take a look at another function, I still find this form. Like here, a lot of different states, a while true loop, and so on.
Okay, so you
So
don't actually have to model that complex data flow at all. You're literally
no,
just looking for like the number of basic blocks, or sorry, I guess basic blocks that are while loops that have a high number of basic blocks they dominate? Is that literally it?
Exactly. Exactly. Yeah. So I wrote
Okay.
also for those people who want to take a look at that, I also wrote a detailed blog post, Automated Detection of Control Flattening, back then, which goes into all the theory in very detail.
Cool. All right. I was gonna say, for those who aren't aware, a basic block dominates another basic block if you have to execute the first basic block to get to the second basic block. Have to. Not may, but have to. So you always go through the top of the loop, for example. You always check that condition before potentially skipping the body of the loop. So that first basic block, that top basic block of the loop, you have to go through that to get to all other nodes. And we track that in Binary Ninja. You can get the current function or current basic block dot dominators. And just pull out these statistics like demos.
So coming back, basically the idea is to apply a lot of different things. And this one important thing here, important characteristics for this entire plugin is it must be fast, it must be easy to compute, and it must be architecture generic.
Hmm.
Because I'm working on a lot of different architectures, and I just love generic stuff and fast stuff. So therefore, these were the design criteria for everything that I put into this plugin. And one other example is complex control flow graphs. While this is for sure, oh no, not this one. This for sure is a complex control flow graph. But not every control flow graph that is complex must have a state machine, like this one. It can also be just have a lot of edges or something like that,
Right,
and a
okay.
different structure. It
I,
can even be loopless.
I was
So,
curious how you determine the main function there from your actual malicious functions in there, especially since it has a pretty high flattening score.
no, right now I'm just in LS. Everything here is
Okay,
non-malicious.
okay.
So if I do it in emotet,
Do you still
like,
get main?
no.
Oh, okay, interesting.
Basically, like every function we see in here, or nearly everything is contains control flow flattening. So in this binary, you don't have to take a lot of
Sure.
effort to find
Right.
flattening function because everything is flattened.
So how often does this generate false positives? How reliable is this?
Well, we can just check that.
Yeah.
So we see the first three already weren't false positives.
Mm-hmm.
The fourth one isn't also. The fifth one, this is a false positive. So this is also false positive. This one isn't. So like what I do is I basically compute a score relative to all other functions in the binary.
Okay.
And to reduce false positives, I basically always just take the top 10%. And the first results have a good likelihood not to be false positives, and then it starts decreasing.
I see. Interesting. Um, so there actually is obfuscation in BitLS?
No. This is not obfuscated code here. This is just
Okay.
normal complex code.
I see. I see. Okay, that makes sense.
If I would which I don't do on a live stream, but if I would put in a commercial application here that is obfuscated, and I would do something like that, we would pinpoint obfuscated code in no time.
I see. So on binaries that actually have these patterns in here, you're not getting that many false positives. As you said, the first
Exactly.
ones are very highly likely, the rest are not. Literally just based on that flattening score. That's really impressive. I never, genuinely never would have expected that. I would have expected things like main to show up there pretty consistently first.
Mm-hmm.
But is that the
No.
case then on non-obfuscated binaries?
Yes.
Oh, okay.
So it's not always main, but let's assume I don't know. I have this plug X sample here. This is a malware sample, which is not obfuscated, by the way. But by applying something like this flattening score in the sample, basically one of these functions, I don't know which one, but one of these functions contains the network dispatching loop of the
Mm,
command and control server.
mm, mm.
So maybe it's even that one. So with basically, as said, most of the stuff in the plugin allows you to pinpoint obfuscated code, but also all other kind of interesting code, which is quite common.
Because code flattening is just a weird sort of command dispatch. It can
Yes.
find other command dispatches, but typically on obfuscated code, it's working well. That's interesting. That's really cool.
So yeah, basically, it's no matter if you look for complexity, for weirdness, or for graph patterns, they all of them might be obfuscated, or they might just be different and therefore interesting. Like looking for complex and colorful graphs is also interesting for fuzzing or for bug finding.
Right.
Looking for large basic blocks, as said, is good to identify inline unrolled crypto and stuff like that.
Okay.
So if you would do that on the Windows kernel, for instance, you would find unrolled symmetric crypto algorithms.
Very interesting. Okay. Large basic blocks, control flow. Interesting. Okay. Is this all intra procedural then, just based on the control flow graphs, not based on the call graph?
This is everything right now. Everything is function local. Yes.
Okay. Very interesting.
So let me give you another example. Let's look for complex graphs, which basically means graphs with a lot of edges, like cyclomatic complexity. We take a look at the relationship between edges and basic blocks.
Okay. So previously we were finding nodes that are loops that dominate a lot of nodes, and now we're just finding functions with high cyclomatic complexity. What does
Yes.
that mean?
So that basically means, like, if you can take a look here, they are sorted again by complexity. 14 or 15, 20 is not so interesting. But looking at the first ones, at some point in time, we always see a gap, like 300, 200, 200, 100, and then it becomes
I
normal, more or
see.
less.
Yeah. Yeah.
So looking at the first functions usually is kind of interesting, but also it might be obfuscated or just implement a complex logic, which is interesting to reverse engineer.
And cyclomatic complexity is number of nodes over number of edges?
Exactly, yeah.
Okay, cool. So we're
So,
finding then graphs with lots of nodes but not so many edges.
could you repeat that, please?
Uh, what types of functions are we finding here? Functions with lots of nodes and few edges, or few edges and lots of nodes, or is that the wrong way to think about
Lots
cyclomatic
of
complexity?
nodes and lots of edges,
Lots
basically.
of nodes and lots of edges. Okay.
Yes.
So, okay, so complex functions then.
Yes, exactly.
Okay.
So
What? Yeah, could elaborate on that. What's interesting then about these high cyclomatic complexity functions?
well, this can be just all kind of complex logic. This can be just nested if and else statements that initialize data structures or that pass something or that perform computations um, or that, yeah, so all kind of complex stuff that might not need a while true loop, for instance.
Okay, I have the complexity calculation wrong. It's the number of edges minus the number of nodes.
Ah, yes,
Multiple.
plus two, I
Yeah.
guess, or plus one.
Yeah. Plus two. Yeah. Plus two. Effectively. So
Yeah.
you're finding. I guess. Yeah. Yeah.
So,
Lots of edges with fewer nodes. Then is what the higher
yep.
complexity ones are.
So, and then we have large basic blocks. I don't think Alice is a good example, but we can try. Plugins.
And
Obfuscation
are
detect.
highly complex functions indicative of obfuscation then? Why is that? Is it because they're chopping up nodes into very small basic blocks and then having a bunch of control flow
So in
obfuscation?
obfuscation, what we typically have is a lot of opaque predicates. Opaque predicate is basically, let's assume we have a function foo, which takes 2 parameters. And normally this function returns just a plus b. So, and the control flow graph would be just a single basic block here. However, the idea is that we have something like this one, which is a very stupid example right now. But let's assume the compiler wouldn't optimize that away in the decompiler. What would happen here is that we get another edge, that we get an ifs and else on the control flow graph, which complicates the graph, but is never really goes into that because
Uh,
this is wrong by design. This can never be by design.
yep.
So, and if you don't have one thing of that, but 1,000 things of that, you have a very complicated
I
graph.
see. Yeah, that makes sense. It's effectively just inserting false nodes and edges to distract you.
Exactly.
Okay, cool.
Exactly.
Thank you for that.
So let me just open that in the background because it will take some while. So yeah, another example is large basic blocks, which basically checks like functions which have a lot of basic blocks in there, a lot of instructions inside a single basic block. That, as said, allows you to pinpoint um, like um, like cryptographic code and stuff like that, but also something which is known as arithmetic obfuscation. Let me showcase that. So here we have a pretty weird basic, like a single basic block function, which performs a lot of computations. And if you zoom in, it performs all kind of weird computations.
Right.
And if you take a look at the decompiler output, the code basically looks like that. This is an
Honestly, not as bad
example.
as I was expecting, but still pretty bad.
Yeah. So this is one example of arithmetic obfuscation. And this typically results in large basic blocks.
Right. Because you're
So
not obfuscating how the code transfers to itself, but simply the um, calculations it's doing.
yes, exactly. So this plugin uses a lot of stuff. It also has some other things like most called functions. This is less useful for obfuscation, but the idea there is if a function is called often by other functions, it might be interesting. And in malware, you often can pinpoint string decryption routines with something like that. Because a lot of strings are encrypted and call another function, that the decryption function, then you can get basically a good hint that it might be interesting to look at. Or if you reverse statically linked libraries or embedded firmware, you also have like memcopy, stringlang, and stuff like that automatically inlined. Not inlined, but included in the binary. And if you take a look at the most common functions that are called, these are typically like library functions.
Yep.
And then you can get some parameters like, okay, these instructions might be library functions. And so you can take a look at them or ask your LLM to name it like a library function or something like that. So this is
Yeah.
often a good use case.
I very often see like log functions in that list. I
Mm-hmm.
think that in particular, this is one of the things that inspired me to go look at the functions that are called the most, but also the functions that make the most calls.
Mm-hmm. And actually, there are two other things which are less related to obfuscation itself, but which are pretty useful in malware analysis. One is the detection of XOR decryption loops. So in this case, we basically look for functions that contain a loop, and inside that loop we perform an XOR with a byte operation. So I have a malware sample here. I have a malware sample which uses a string decryption routine. It is Mirai. This is an embedded botnet. And what I can do is, if I let me clear that stuff here. What I can do is I go to plugins, obfuscation detection, and then XOR decryption loops. It will basically find me one example, and if I take a look at that, the decompiler, I'll find here that we have a loop where we walk over a byte array and XOR each byte array with this hard-coded constant. So this is a string decryption routine. And we just found that function just by executing this heuristic.
Beautiful. And it's fast and it runs on every architecture.
Exactly. And based on that, there's also one other thing. Like, do you know what is the most common crypto algorithm used in malware?
Is it XOR?
No, actually not. It's
Okay.
RC4.
Okay.
So let's take a look at RC4. But please, the English version. So RC4 is doesn't have magic constants or stuff like that, so you can't easily detect it by looking for magic constants. But it has one specific characteristic which made it pretty unique to pinpoint. If we take a look at this KSA part, we have basically two loops, and both of them are taken like 256 times.
Interesting.
So what we basically have to look for as a heuristic is function has two loops, and function uses the constant 256. So we don't even have to check if this constant is part of the loop bound. This would be way too expensive to check that. But just checking for all functions that have two loops and use this constant, this is quite cheap. And if we do so, for instance, let me open some malware sample, which implements RC4. So plugins, obfuscation detection, utils, and then RC4 implementations.
Okay.
Then it finds this KSA here. And if we take a look at that, and here it finds two KSAs, one of them is a false positive, the other is not. So if we take a look at this one, and we check, okay, we have two loops, one loop, second loop, and both of them are taken 256 times. So
That's pretty neat.
yes, and the other part of the algorithm, the PRGA, this one is often nearby. So we can take a look. This is case A. And we see, if we check the cross references, we see that call here. And if you take a look at that code, this one basically has also been identified by, where's the log window? Here, this function actually has been has then be also noted as PRGA, which is exactly that function here. So it basically was able to pinpoint both functions. The second one was basically in a loop, we do some modulo operations. This is basically the thing we check in here. And that this one has significantly more false positives, but finding the case is most of the time very straightforward and cheap.
That's pretty incredible. Do you happen to remember how you detect if there are loops in a function and how many there are?
Well, I wrote my entire own loop analysis for that. So in the obfuscation detection folder, the code, we have loop analysis.py, where I compute natural loops, back edges, the natural loop body, but also strongly connected components, loop nesting trees, and so on and so on.
Oh wow,
So
okay, yeah. So it's not that simple. I was
it's
thinking
not,
maybe it
well,
was just the trick with dominance.
yeah, it's basically a bit of graph theory, but yeah.
Yeah, interesting. All right. That's neat. So
So
then you can identify functions based on the number of loops they have, which is crazy. Are you
mhm.
literally matching on that 256 number, or do you also check like if it's 255 and they do a
No, I only check for 256.
oh, okay, interesting. So if it compiles slightly differently, you might miss it, but
Yes, exactly. These are
okay.
just heuristics, but they work pretty stable normally.
That's pretty cool. That's really cool.
So if you're just where you're asking for loop nesting, I have indeed a characteristic um, where I look for high loop frequencies. Like I sort functions by the number of nested loops and stuff like that.
Yeah, I'm gonna have to take a look at that. I've been meaning to see if you can calculate a loop sort of depth based on just the dominance frontier thing, but it looks like it's more complicated than that.
Well, for loop nesting, you have to compute loop nesting trees, but this is a different story.
Yeah, okay. Not something I've yet worked with.
Mhm.
But sounds interesting. I'll have to take a look at that.
So this is the first part I wanted to showcase. Basically, basically how to detect code obfuscation. As said, the idea there is that we look for complex, weird code.
Yep.
And turns out, besides looking for obfuscated code, it has all kind of other characteristics to find interesting code in non-obfuscated software. So in fact, I built that initially with exactly that goal, and nowadays it's my go-to. So the first things I do when I shoot a binary is first I take a look at the imports, I take a look at the strings, and I shoot some of the metrics to identify interesting stuff.
Yeah, no, that's amazing. So you've walked us now through the complex obfuscations, the large control blocks. We found some specific patterns.
Mhm.
Have we seen just weird ones too? Which one was the one that
No,
helped us
weird
with
ones we
weird?
didn't see. Weird ones, so basically arithmetic obfuscation can be
Oh,
considered a
okay.
weird one.
Sure. Instruction level obfuscation.
Exactly. Like uncommon, like it's weird ones just to get the intention. In unobfuscated code, you have a lot of common patterns, like a lot of move instructions, move call, function prologue, function epilogue, and stuff like that. Like you have a statistical you have basically a statistically very common instruction sequences,
Hmm.
and you can then let me just showcase that. Um,
Yeah, while you're looking for that, one of the things I often encourage my students to do is actually go through a binary, count all the instructions, and build a histogram. See what the average basic block length is for functions you look at. See
mhm.
what the common instructions that get used are for the functions you look at. And then highlight things, alert, whatever it is, when you find things outside of what you expect them to be.
Yeah, exactly. So here in this file, I basically have for various architectures, like for the four large architectures and for IL level, for low level IL, I basically computed on a large data set
Oh,
the
wow.
1K most common mnemonic sequences, like add, compare, move, call, move, and stuff like that.
Hmm.
So And then I can basically walk over all functions, take a look at the most common sequences there, and check which functions do not have the most common sequences a lot. And that way, I get like statistical deviations or functions that use uncommon patterns in a statistical meaning, and then they might be interesting.
Okay, so this definitely goes a step beyond what I was suggesting. Why are you able to find, or sort of what are you able to find from this that you aren't able to find from just individual, mnemonics?
Um, it allows you um, to detect specific patterns sometimes, which might be small functions that might not be like too complex or stuff like that, but still perform some weird computations. So like often some obfuscation helper functions, like initializing some data structures, for instance, or some weird compiler optimizations, some weird calling conventions, stuff like that.
All right, that's interesting. And how did you decide on these patterns?
Um, of these hard coded here, you mean?
Oh, these were just hard coded that you chose, or did you find the most common like sequences of
These are the most
three?
common ones. Like I had
Okay.
like I had like I had a database of I don't know 2 GB of binaries from Windows, Linux, and stuff like that, compiled with different compiler optimizations and stuff like that, like a pretty large data set that has been analyzed for the like there we have basically extracted the most common instruction sequences and yeah, and then just put sorted them by frequency and put out the most common 1K ones.
Right. And did you play with the context window there? It looks like we're just working with three at a time, but what did it look
Yeah,
like at four
well,
and five?
yeah, well, it's often like this is basically called n-gram analysis. This comes from NLP, NLP and language analysis and stuff like that. And three is often if you go too high, you get too specific. If you go too low, it becomes like noisy a bit. So three is a good ground. 3 to 5 is mostly used and stuff like that.
Interesting. And I'm remembering now that there's been some research I've read, Asymptotic, I believe it was, that was trying to do a similar thing, trying to predict the next two or three instructions, based on the current one to see if the actual program is doing something weird based on those engrams, as you said. Interesting stuff. I
Mhm.
haven't taken a look at that in a while, though.
By the way, for that, there's also an entire blog post about that, which goes quite deep into the stuff that we do. It's basically the statistical analysis to detect uncommon code, which goes deep into the theory behind that one.
Good. That's probably an awesome read, I imagine. I'm gonna put that on my reading list.
So after we found some interesting stuff, we want to analyze obfuscated code. So, and analyzing obfuscated code, well, there is no clear way how to approach it because it's basically very complex and can take a lot of different forms. Control flow obfuscation, virtual machines, arithmetic obfuscation, and stuff like that. So you basically have to detect the kind of obfuscation. Then you have to understand the pattern, and then you have to work on automation to remove or simplify the pattern. So this is the main idea. And what that means can be all kind of stuff. This can be just compiler optimizations, like that you take a look at the decompiler and hope it gets cleared with the dead code. It might be that you have like broken jumps or broken disassembly. It might be that you have to have control flow obfuscation and need to patch the binary to
Mhm.
simplify the control flow, like patching.
Is
It
that
might be that you
usually
have
how
to remove.
you, sorry, is that usually how you recommend getting around what you were showing us earlier with the flattened control flow? Just literally patching the binary to make it easier to read.
No, for flattening, I mostly recommend not to touch it at all because you can often see in flattening, you have the good thing, you can first often see what is going and still can understand a lot of stuff in the binary because the original basic blocks remain the same. You just have the control flow obfuscated, and dynamically you still see where the trace goes. Like if you combine it with something like time travel debugging or stuff like that, control flow flattening isn't really something you have to deal with. So still, if you notice, if you have like a motet, like an entire malware family, which always uses the same obfuscator, then you want to write mostly on the decompiler level a transformation that undoes that. And I think Binja has something like that for one specific obfuscator since a few weeks.
Yeah, we added an example on how to just reorder the basic blocks
Yeah.
ad hoc. There, that does lead to the question in chat here. Is it possible to mostly automatically infer enough about control flow flattening to automatically rewrite the control flow back to normal?
It depends on the implementation.
Yeah.
In easier implementation, yes. In more complex implementation, not so much.
Yeah, so there are well-known control flow level obfuscators, and
Yes.
we wrote a deobfuscator for one of them, and you could write a deobfuscator for others as well.
Yes, exactly.
I think there was another question in here. Oh yeah, does broken disassembly mostly crash the program, or are there also exceptions for
Let me broken disassembly showcase in some minutes. Like in
all right,
5 minutes, I showcase an
perfect.
example. But no, it won't. In short, it won't break the execution because it's just basically the disassembler recognizes something as a function which isn't a function. That's basically the
Mm.
problem.
Though that said, there is also a signal for a instruction it fails to decode, I believe. So it could also catch that if it wanted to, but that's not what we're
Mhm.
talking about today.
So patching or removing stuff, and it will like maybe you want to need like the shotguns, like symbolic execution, SMT solving, and so on and so on. I didn't go much into details here because it would basically too expensive here. But all of this stuff will be part of my trainings. But let's focus on some basic stuff here. So um, I wrote. Let's say depending on the analysis, you might need a few helpers that allow you in very specific use cases to simplify some stuff or so on. And over time, like in May this year, I published the first version of this new plugin. In October, like a month ago, I published the second version of this plugin. So it's rather new. It only has 3 features right now, but more of them will probably come over time.
Yeah, but they're
And
pretty cool features.
yeah. And the idea there is basically to provide some generic helpers that might help you in various deobfuscation or in general code analysis contexts. And one of the things I would like to showcase first is broken disassembly. So the plugin itself is called, while the first one is called obfuscation detection, this one is known as obfuscation analysis, and it's also in the plugin inventor and stuff like that. So, and one example is broken disassembly. I have a sample here which has a lot of different functions. Let's take a look how many functions it has. Let's say len bv.functions. It has like 1K functions more or less, 950 functions. And this obfuscation works by they create a lot of code or a lot of data that is designed in a way that the disassembler understands it as code and tries to disassemble it. However, a lot of functions are just useless.
Hmm.
So I have this plugin, obfuscation analysis, which allows you to identify and remove corrupted functions. Let me go to identify. It will then find a lot of functions which are just bullshit. So let's just take a look at one and look at the assembly code. And here you see doesn't make much sense.
Yeah.
Let's take a look at the other ones. Here also it's broken and stuff like that. So a lot of broken stuff. So, and they basically a lot of waste here. So what we could do is now we go to plugins, obfuscation analysis, corrupted functions, remove. Then it will remove them. And if we take another look, we now only have 600 functions. So it removed over 300 functions that were just broken. Gives you a significantly better way to deal with.
That's very interesting. Binary Ninja will usually create a function if it thinks one is there, which is typically pretty harmless, except for the fact that it can waste a lot of your time. If you wanted to impose, I suppose, sort of less conservative assumptions into the binary, that we can ignore certain functions because they have certain attributes, you can actually change Binary Ninja's workflow engine. After function detection, you could run your own module and reject a bunch of things. This is less specifically for you and more for the audience at large.
Ah yeah, nice. Let's just for fun, let's look at this example for complex functions and see what we find there. We see a lot of stuff is 3 or 4, and some of them 79. And so, yeah, we for sure have some more complex functions in here, and they are probably interesting to take a closer look at, assuming we would want to dive deep into this obfuscation here. But for now, let's just skip that. So one feature is the identification of broken disassembly and the removal. Another feature can be the inlining of other functions. So let's assume we have a function. Let's assume we have a function foo, which performs something like return bar plus bars. And let's put in some values here. And let's say we have int x and y. And let's assume like bar implements something like return x plus y. And let's assume we have bars, which returns x minus y.
Yeah.
So if we take a look at this function in the decompiler here, we see basically this one returns x plus a bar called bar, x plus y plus that. And the decompiler cannot really simplify that. However, what we can do in the decompiler is we can inline functions, and we can inline functions in a recursive way. So if we would inline them in a recursive way, it would, in this case, look like x plus y plus x minus y. And then the decompiler would be able to simplify this code, because it inlined everything to the same function, and would be able to basically make something like that out of that.
Right.
So this, in some cases, this can be a very useful feature. So let's take a look at that. Let's go, for instance, to the emoted sample. And let's take a look for a smaller function.
This
Just
is an example of where the obfuscation would make the binary a lot slower because it's having to
yeah.
do a bunch of redundant and unnecessary calculations.
Yes. So this is a small example function, which in the decompiler output, let me stick it to single view. So, where the decompiler just calls two functions. And now, well, I'm not in the medium level, on the high level. So, and now I can go to plugins, obfuscation analysis, inlining, and then I have two options. I can inline them recursively in an indefinite number of ways. This would walk down the entire call chain, the entire program from that function, and inline everything into a single function, which can be useful sometimes, but for larger binaries, it will just explode. So for this case, we also have the options to inline it up to n levels. And this n can be actually set in here. And by default, it is set to 1.
Okay.
So, and now what we could do is we could, for instance, do plugins, obfuscation analysis, inlining, inline up to n levels. And then it basically inlines the entire function, and now this one looks like that.
That's amazing. This is really cool. We were talking about this at Recon, and I'm glad to see it actually come to fruition. Um, so then I don't want to jump the gun, but now I'm excited to see the next step now that we have the functions inlined.
Yeah. So this basically allows you to enforce the decompiler perform optimizations on a cross-function level. And there are not many use cases where this works nicely, but there are some where this can be very, very useful.
Right, yeah. Um, Often inlining functions to their call sites, what we call that in general would be context sensitive analysis, and it usually is more computationally expensive, but allows us to produce more specific results, usually, because we're analyzing the function in context. You get to see all the inputs and everything, what gets used, what doesn't, and we can simplify it how we need to.
So now I would like to showcase the last feature, but introduce before something which is called arithmetic obfuscation, or mixed Boolean arithmetic. So the idea is pretty simple. We have a function foo which gets end x and end y, and it returns something like xx or y plus 2 times x and y. So this one is basically the same as return x plus y. It's just a simple computation of x and y. However, it looks more complex. And this is called arithmetic obfuscation. And this one is quite cumbersome to analyze. And in some cases, it can be analyzed in a good way. In other cases, it cannot be really simplified.
Mm.
So, and at Recon this year, in June, we basically gave a talk about this plugin. And this is the first time we introduced this plugin then. Where we basically introduced for very simple forms of MBAs, where we are able to simplify them. For that, we use a combination of the high-level IL, backward slicing, and feed it into a custom solving engine that is written in Python to solve like arithmetic obfuscation. So we basically extract large computation slices from the high-level language and feed it into custom solver, and then the result is added as a comment. So to showcase that, I want to showcase it first on an artificial example and then on a real-world binary. On an artificial example, here we have 6 functions. This is one pretty small MBA. Code looks like that, but still not very clear what it does. So what we can do is we can go to obfuscation analysis, and then MBA simplification, and then slice and simplify. And then it will basically simplify it like it's 2 times arg3 minus arg1. That is the simplified version.
Amazing.
Let's
And it just adds it there as a comment, the whole thing that it's actually doing.
Yes, exactly. So here we have some other computation. So we can then do something like plugins, analysis, simplification, simplify. Then here it wasn't really able to simplify that because the slicing didn't probably end up very well. Okay, this happens as say this is a very hard problem here. Let's take this one. Well, it's still simplified, but it's not as simplified as it could be. So in this example, for instance, we can go plugins, analysis, simplification, that, and then it's basically a more complex computation. And actually, this is nearly its shortest form. So it's just a very semantically complex expression and just hidden in a even more complex
Yeah,
computation.
interesting. It's cool that it's still something that's not like super super simple. It's still somewhat complex.
Yes,
But it's certainly easier to read than what was there.
yes.
And yeah, I definitely recommend anybody watching to give Tim's talk from Recon a watch too. It was one of my favorite talks from this year. Yeah, this year. Wow.
Okay. So after we've done that, let's put everything together. So I've brought a binary, actually North Korean malware sample. And if we take a look at one function, for instance, we find, let's take a look at the control flow graph first. We see we have a lot of large basic blocks, and we have a lot of weird computations here. So this looks like arithmetic obfuscation. And what we can notice, remember, obfuscation is about pattern matching. We have a lot of large basic blocks that perform weird computations, and all of them end on some kind of conditional jump. So what might be the case here is that we have something like opaque predicates here, but instead of having stuff like that, we have an MBA over stuff, and not sure what's in there. So like we have an MBA, we have two MBAs that we compare to each other, and they are then the same or not the same. This is just a working thesis right now. We don't know, but what we see is we see a lot of conditional jumps, and all of them follow the same pattern, like weird computations and then a condition. So one thing to check would be, we go to the decompiler output, look at a formula like this one, and just apply our plugin and check if this MBA folds down to a constant or not,
Oh,
like 1 or 0, because this is arithmetic check, which can be true or false. And if we are able to simplify that arithmetically to true or false, then we know it's an opaque predicate, that we always take it to the one or other direction. So let's verify that. So it's working. I think the problem is that it still analyzes the binary. Let me stop the analysis,
yeah.
because normally it just does take 1 or 2 seconds.
Yeah, with all the other binaries you have open too. You might want to close out some of those,
Oh yes, well, let me just close it out.
especially if any of those are running in the background.
Indeed, it did stuff. It added for in fact a comment, it's 1, so this one folds always down to 1. So now we have a proof that this can be controlled, that this this is basically an opaque predicate based on MBAs. Let's
Oh.
do double check here. Let's take, for instance, this one. Not sure, maybe the plugin is broken and that case doesn't work. Happens. You see the computations are also quite large, so don't really know what will be the outcome here. But at least we have one working hypothesis that has been confirmed.
Yeah, that's
So,
really interesting.
so
Yeah.
now our goal will be, no matter what the result here be, we have one true case where this holds, would be to write a script that detects all opaque predicates here, solves the direction if we always take the jump or if we never take the jump, and then automatically patches the binary. This would
Right.
be our goal here.
Right.
So I've prepared something which uses a combination of symbolic execution and SMT solving. I don't showcase how it works in detail because this would explode here today, but I want to give you the main idea. So symbolic execution, the idea is if we have code like this one, so like this one, we can transform it into an intermediate representation, to a low-level intermediate representation. So for instance, like RAX equals RAX plus RBX, and then RAX equals RAX plus 10, and then RAX equals RAX plus 20. And then we define a key value lookup or a hash map, dictionary, whatever you call that. So the idea is we have a state S which maps keys to values, for instance, RAX to RAX and RBX to RBX and so on. And we would then rewrite that stuff. So like it would look like, for instance, that one. And here. So the idea is that we have an evaluation, a propagation, and an assignment. So we will go instruction by instruction and propagate the current values from the state. Like we have the state and we look up RAX, which is RAX, and propagate it into here. And then RBX, we propagate the current value of RBX in here. Then we could simplify it, but here in this case we cannot simplify anything. So we move that and assign that to the state. So basically here, this RAX would be now RAX plus RBX. Now we have this instruction. This one would take the current state of RAX, which is RAX plus RBX, propagate it in here, and would add plus 10. And now this one gets assigned to that value. So this one is now RAX plus 10. And now here, the same. This one would be assigned plus 10 fee. However, in this case, we have a simplification rule that detects we have two constants, and these two constants can be folded together. So like this would be RIX plus RBX plus 30. Now it is simplified, and we store it into RIX again. So, and now this state map contains the entire computations that have been performed by this instruction sequence. That's the idea of symbolic execution. And the idea now would be that we have, if we have that code, that we symbolically execute this basic block from that instruction down to the conditional jump. And once we executed that, we have a pretty large symbolic formula. And then we have some large arithmetic condition And if this is true, we go to the true case. Otherwise, we go to the false case. So, and this is like our next block. So this is our condition. And the next block is if the true case holds, we return Z1, otherwise Z1. And now we derived that symbolically. What we could do is now use an SMT solver. An SMT solver is basically a mathematical logic solver that basically takes conditions and gives you a solution if it exists. So it basically tells you two answers. It gives you basically two answers. One is a solution exists. The second is a solution cannot exist. And if a solution cannot exist, we basically know that this case can never be taken. So the idea is we basically ask an SMT solver then, this should be equal to the true case. And in this case, if the SMT solver tells us this is not possible, like this expression can never evaluate to the true case, then we know we have a conditional jump where only one way can be taken. And if only one way can be taken, there's no need to have a conditional jump there. It's an opaque predicate. Like it's the same thing as if 1 equals 2, just a more complex. So it's just bullshit. So what we could do is then, if we have something like if 1 equals 2, what we could just do something, we could just remove that. It's just that code. So in this case, if we know, we can basically just knob the instruction, or we could always jump depending on the case, on the direction. We don't know yet, but this is the idea. If we symbolically execute it and ask an SMT solver if we can take both directions, and it tells us we can only take one direction, then we know, oh, there's no need to do that here. So it's an opaque predicate. And so there's a script which which uses the miasm reverse engineering framework. As said, I won't go too much into details, but it will basically disassemble the entire function. It will symbolically execute each basic block, check with the SMT solver if the jump can be taken into one or both directions, and if it can be taken only into one direction, it will flag it's an opaque predicate and print out the binary ninja API to always branch or never branch. So basically here I have two functions. I have bv.alwaysBranch, let's say current address. And if I do that, it would just knob it. And never branch would do the opposite. So this is the primitive set that we will use now. And let's see what's going on. So the script takes as input the binary and an address. As address, we would put the start address of the function. So we go to samples and opaque malware. By the way, all these samples are used here. All of them are included in the example repos of the two plugins I just showcased. So we take this address and put it in here.
Okay.
And it detects some opaque predicates.
Wow.
So let me filter only for BV because I'm lazy. So it detected 10 opaque predicates.
Oh, funny. Okay, interesting. Yeah.
Now I can put it in here. And then I put it in here. Let me just scroll out to see the difference. We have it like that. Then I hit enter. And it patched it like that. So now we have a lot of straight line code. However, we still have some conditional jumps. And we take a look at this one. This looks pretty much strange. So this is probably also an opaque predicate. So it's basically, this is an opaque predicate which has been spread across two different basic blocks. Now we patched one jump, so we merged them into a new basic block. So now it's propagated here. So what we can do is we can save the file as a patched file, save as, and do something like opaque malware patched, and redo the same stuff and see if it still finds opaque predicates or not. So while we take the patched file, and it still finds 3 opaque predicates. So again, we grep for BV.
I'm incredibly amused by the fact that you're just printing out the commands to paste in the console.
Yeah, well, and then we put it in here. And this time it just deleted that. And now we can take a look at the decompiler output. And we see it's really straight line code now.
Yeah, that's not so bad. Or not as bad as it was.
And it still has MBAs, but
Yeah,
it's
still
straight line
lots
code
of
now.
awful constants in there.
So what we could do now is we could, for instance, here, okay, this is a function call, and it has some parameter, and we see this parameter is an MBA. So what we could do is we could here go plugins, obfuscation analysis, slice and simplify, see what it does. It folds down to 1.
Brilliant.
So this one folds basically down to 1. And
what
now,
a demo. That's incredible.
Now we can apply a trick in Binger. We notice we have RAX65. What we can do is we can go to the medium level IL, note that it is always 1, and in Binger we have something which is known as user-defined data flow. So that basically allows us to define assumptions about variables. Here we can, for instance, assume that here set user variable value. We can assume, so like it's a constant value and it's always 1. We just saw that. And once I hit accept, it will basically add an assert. And this assert allows the decompiler to assume that this value is 1 and basically propagate the value into the decompiler. And there you see now there's only one constant left. And now we could do the same thing. I could do here that one, plugins, obfuscation analysis, inlining. Not inlining. I need to go on the decompiler. So now RX65, this one has been optimized away here, only that one remaining. So I can take this one, go to plugins, obfuscation analysis, BA, slice and simplify. Let's see what this goes. This is also 1. So I could do the same thing. I could go here. That was that one. Then I could go here, go set user variable value, set it to constant value 1, hit accept. And now if I go back to the decompiler, it would just propagate the 1 in here. And that way I could, if I would be interested in doing that, do it for the other things too. And other functions, also, this is just another function, uses basically the same kind of pattern. Like again, MBA-based opaque predicates. So like we have a lot of functions in this binary which use the same obfuscation technique all over the place. And your role is basically pattern matching, like I've seen here today. The idea is to detect the kind of obfuscation, understand the pattern, we detect the obfuscation, MBAs, control flow flattening, and sorry, MBAs and opaque predicates, understand the pattern. Well, it's used to hide the control flow all over the binary, and this is important, it's local to the basic block level. So, solution, we work on automation to remove and simplify the pattern. And yes, honestly speaking, I did a lot of manual steps, but in theory, you could automate it even further. So we automated the detection part, but in theory, I could just run that in the background in Binja and automatically execute that and so on and so on, and do it also in an iterative way, and then it would be way simpler. But for demonstration purposes, that way was a bit better here. And yeah, this is one example workflow how you could approach an obfuscated malware.
Honestly, truly beautiful. That was a fantastic demo. Being able to see that iterative process and not having it do it for you automatically, I think is very, very at least important to see once, because a lot of these things are done for us automatically and we just don't see how they're happening in the background. So being able to watch you do it, watch it work iteratively, see the theory sort of prove itself out was really cool. Thank you for that.
Thank you.
Um, was there anything else you wanted to show us with either of these plugins?
No, that was basically all of the things I prepared.
No, that was a beautiful demo again. That was
Yep.
incredible. Worked really well. I do have another question from chat that I missed
Mhm.
earlier. But we will be wrapping up in a couple minutes, guys. So if you have any last questions, get them in
So
chat.
absolutely, just feel free to shoot any question you have.
Yeah, drop them in chat. You can send them to Tim after the stream. There's one I have here though. If software obfuscation is based on constant values, returned by OS API functions, that we are certain will return the same values across the entire operating system. So if you have, I guess, just pure functions, that'll always return the same
In
constants.
in the early 2K, like 2000 until 2005, in Windows 32-bit code, there was quite common code like
Hmm.
something like that. And if we take a look at good code process, sorry, that's English, that's German. Yeah, still German, but here we have it here in Stack Overflow then. Why does it always return -1?
Right.
So yeah, we do have API functions that return constant values, and then and then this can be used as an opaque predicate. And in this case, the example from before wouldn't work, because what we did here was symbolically executing code that we have on the basic block level and then feeding it to a solver. If we work on API functions, we would basically need to encode the logic of the API function. Like in this case, we would hook the function and know if we call that function, we have to return -1, or like put -1 into array_x, for instance.
Okay. So the end of that question there is how can you deobfuscate things without emulating the entire OS? And it does sort of seem like you need to choose some set of values to try, or actually just run the function or whatever it is, right?
Exactly, yes.
Yeah. Yeah.
It always depends on the exact case. There is like, often there is no repeatability. So if you have your set of tools and techniques, you can often copy these parts and stick them together and put some glue code around. That's basically a very common use case. but that you can use one script and use it as it is on
Right.
another binary.
Right.
This would be nice, but this is barely the case.
Yeah. Yeah. This question also has me thinking about like you were symbolically executing individual basic blocks because data flow dependencies get rather complex among basic blocks.
Exactly.
So, like, what research gets us in the direction of being able to symbolically execute multiple basic
Yeah.
blocks?
Let's assume these opaque predicates would not have been local to the basic block,
Mm-hmm.
but depend on function arguments that have been passed along the call chain.
Mm-hmm.
That way, we would be required to do some kind of global or at least a cross-function analysis. And you already see what kind of effort it is to deobfuscate something like that here.
Yeah.
So doing it cross-function, let's say, is a bit of more work.
Yeah, no, I've seen some research in that direction where basically it inlines function calls to some number of depth, usually
Mhm.
a depth of 2 or 3, and then figure things out from
Yeah,
there. But
exactly.
it is computationally intense to reanalyze every function at every call, all
Yes.
the code for that entire function every time. It gets big.
Yes.
All right. Well, thank you so much for everything you had to show us. Was there any last things you wanted to say or show or anything like that?
Yeah, well, thanks a lot for all your attention and for interest. And as said, if you're interested in learning more stuff about that, check out the plugins, check out the blog post, check out my website. There's a lot of stuff. Also check out Roll stuff, which is also very nice. And maybe it would be nice to see you in my training.
Yes. If this has piqued your interest and you'd like to learn more from Tim, you can sign up for his class in the description. I put the link. You can also go to re-verse.io and check out the rest of everything for Reverse. Remember that tonight is the last night to submit to Reverse's CFP. So if you have any interesting research, we would love to see you at Reverse. Get that in tonight. And 5.2 came out today. So go around, play with that. Go download Tim's plugins, experiment with them, ping us after the stream, let us know your thoughts. But I think that's all. So thank you all for sticking around. Thank you, Tim, for being here. It was a pleasure to have you. Fantastic
Thank you, Kyle,
stream.
for hosting me.
Of course. And I'll see everybody maybe in 2 weeks. We'll see. I'm not 100% sure what the stream schedule is going into the holidays, but thank you all for sticking around, and we will see you next time. Goodbye, everyone.
Thank you. Goodbye.
Go to outro.